Today we're going to continue our idea of factoring trinomials. Remember, factoring is we're breaking it down into smaller pieces. So we're going to learn just one new method, and this method is super easy, and it's for what's called a special cases. So before we get started on that, let's just review some squares. So 1 squared, if you think about this, we have this whole table of squares up here, which you might know off the top of your head. But in case you don't, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, and 10 squared is 100. So just knowing those numbers is going to come in handy today. So we are talking about the difference of perfect squares. So in this case, the word difference means subtraction. So it has to do with a subtraction problem. And perfect squares are things of, I'm going to give you some examples because they're easier to understand. An example of a perfect square is 9, because 9 is 3 squared. Another example of a perfect square is 25, because 25 is 5 squared. So all of these numbers up here, 1, 4, 9, 16, 25, 36, 49, 64, 81, 100, they're all perfect squares because they are all a number times itself. It's also important to note that x squared is a perfect square because it is x times x. So that's going to come in handy. So we look at this problem. It says to factor the polynomial, so notice that it has 2 terms in it. So that's really key. So every single problem that you're going to factor using this method, what's called the difference of perfect squares, is only going to have 2 terms. It has 2 pieces to it. Okay? That's very important. So the second thing that's important is because this is a difference of perfect squares, that means it has to have a minus sign. So if we look at all of these examples here, notice that all of them have minus signs in the middle. So these 6 examples, first of all, take care of this difference part. So the difference of perfect squares means that both the first part and the second part are perfect squares. Well, one of the examples we gave for the perfect square was x squared. So what that means is that s squared here is a perfect square because s squared is s times s. And hopefully you know that 49 is a perfect square because it is 7 times 7. So when I go to factor this, the way these factor, and it's a trick that kind of works every time, and mathematically there's a reason why, but what happens is you take one of each of the s's and put it in the beginning, and one of each of the 7's and put it at the end, and every single time you do this, you end up with 1 plus sign and 1 minus sign. And that is your factorization of s squared minus 49. So notice that one s went here, and the other s went here. And the same thing was true with my 7's, that the first 7 went here, and my second 7 went here. And then every single time, just always, 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 I'm going to have 1 plus sign and 1 minus sign. That's just the way these factorizations work. So let's look at the next problem. I have t squared minus 81. Well, first of all, we know that it's a difference because there is a minus sign, so that's helpful. The t squared here, well, that's a perfect square because it is t times t. And 81 is a perfect square because it is 9 times 9. So when I go to factor this, I will have parentheses first of all, 2 sets. In one parenthesis, or in each parenthesis, I'm going to have a t. I'm also going to have a 9. And then in one of them, I'm going to have a plus sign, and the other one I'm going to have a minus sign. Remember that one of my t's comes from here, the first t comes there, and the second t goes in the second parentheses, and the same is true with my 9's. The first 9 goes in the first parentheses, and the second 9 goes in the second parentheses. And every time without fail, there is always one plus sign and one minus sign. It's just the way it works. So looking at number 3, we have 16 minus x squared. Well, we know this is that 16 is 4 times 4, and x squared is x times x. So this is a difference, because there's a minus sign, of perfect squares, because each is a perfect square. So the way this is going to factor, do my parentheses, and I'm going to have a 4 in each of the parentheses, and I'm going to have an x in each of the parentheses, and I'm going to have a plus sign and a minus sign. Now, if you look at problem 4, it says 4g squared minus 25. So this one looks a little bit different, because notice here it doesn't just have a letter squared, it has a number and a letter. Well, if I look at each piece of that, like starting with the 4, well, 4 is 2 times 2, and g squared is g times g, and then 25 is 5 times 5. So this is still a perfect square, because every single piece of this is in fact a perfect square. So I'm going to go ahead and draw my parentheses, and I'm going to take one of everything and put it in the parentheses. So I'm going to have a 2 and a 2, and I'm going to have a g and a g, and I'm going to have a 5 and a 5. And then one time it's going to be a plus sign, and the other time it's going to be a minus sign. So it's really no different than the previous problems. So what I want you to do is I want you to pause the video, and I'm going to do problems 5 and 6, and then when you unpause the video, the answers will be there. Let's see how you did. Factorization for 5, which was originally 36h squared minus 21, becomes 6h plus 11 times 6h minus 11. So I've already done my squares right there. I figured out what the square roots were, and that's where the factorization come from. And the answer to number 6, which was 81 minus 49k squared, is going to be 9 plus 7k and times 9 minus 7k. So we're going to kind of put all of this together and just kind of go through some steps for factoring. So the first thing you always do when you start factoring is you look for a GCF. You look for a greatest common factor. So that's where you see if you can divide all the pieces by something, which we're going to do some problems like that in a second. The second thing is you figure out, is it a difference of perfect squares? So remember, a difference of perfect squares, we said this a second ago. It's important to note it's only going to have two terms. They will have a minus sign in there, and it will be a perfect square. Each piece will be perfect squares. Okay. The third step is to use what we call the AC grouping method, which we're going to review, what we learned last time. Okay. And it's important to know that when you go to solve, so solving is the final step here. All of our equations must equal 0. In order for us to solve, they must equal 0. So I'm going to do problem 7. It says I'm supposed to factor out the GCF and then solve the equation. In order for me to factor out the GCF, I have to take this problem, 2g squared minus 26g, and I have to prime factor this. Well, 2g squared is just 2 times g. And then if I take 26 and I prime factor that, 26 is 2 times 13. So minus 2 times 13, g equals 0. So then I'm looking for what these pieces have in common. So notice both parts of this, the 2gg minus 2g times 13g, both have a 2 and a g. So I'm going to take out that 2 and that g from each of those, and I'm left with g minus 13, and it still equals 0. So this, what I've done so far, is the factoring part. So this is the factoring part. If I need to now go ahead and solve this, which is the next step, in order to solve this, that's where I have to use some math. And I say, okay, I'm going to take my first part of my problem, 2g, and I'm going to set it equal to 0. And I'm going to take the second part of my problem, my g minus 13, and I'm going to set it equal to 0. So looking at the first part, I need to get g by itself, which means I want g's on one side, everything else on the other. Recall that whenever I have a number in front of a letter, they're being multiplied. There's a multiplication symbol there. So to get rid of something that's multiplied, I'm going to divide both sides by 2, and I end up with g equals, well, 0 divided by 2 is 0. So that's one of my answers. And then for a second problem, if I'm going to solve this, I need to get rid of, I'm going to get g's on one side and everything else on the other. So I need to get rid of this minus 13 by adding 13 to both sides. And 0 plus 13 is going to be 13. So my answers to this problem are that g equals 0 or g equals 13. So both of these would be answers to this problem. So I want you to notice that when I solved this, I did two things. All of my factoring, this part up here, was done in pinkish color, and all of my solving was done in green. So if you're trying to figure out which part is which, I color-coded. The factoring is the pinkish, and the solving is the green. I just used different shades. So I'm going to Problem 8 is going to be very similar, but the very first thing that we have to do is, in order for us to solve this, remember, we set up here the equation must equal 0. And if you notice, this equation down here does not equal 0. So that needs to happen first. So in order to get this to equal 0, I need to get rid of this 30w. So I'm going to add 30w to both sides. These cancel, and I am left with 3w squared plus 30w now equals 0. I cannot combine these two together because this one has an exponent of 2 and this one does not. So I'm going to leave the problem like this. So I'd like for you to pause the video and see if you can do this on your own. When you unpause the video, I will have the factorization done in pink and I will have the solving done in green again. So after prime factoring, I ended up with the problem 3w times w plus 10 equals 0. And I set each piece equal to 0, so 3w equals 0 and w plus 10 equals 0. And I ended up with answers of w equals 0 or w equals negative 10. Those are the two choices I came up with. So on the back, it asked me to factor using the ABC method. So again, when I do these problems, I'm going to do all of my factoring in pink, and then I'm supposed to solve this. And when I go to solve this, I'm going to do all of my solving in shades of green. I'm actually going to do problem 10 first because 10 is going to be harder than 9, and then I'm going to help you set up 9 and let you do that one on your own. So this is what we learned in class last time. So remember, I can't break this down. There's nothing that all these pieces have in common. So I have to rewrite this with two different parts. So I'm going to use the table. So I'm going to draw out my table. Remember, my A is what is in front of x squared. My B is what is in front of x, and C is the number by itself. So I want to go to y equals, and I want to do 6 times 4 divided by x. That's what I want to type in, y equals. And then because I have a negative sign in the problem, I want to go look for my negative whole numbers. So starting with negative 1, you will have negative 1 and negative 24. Then you'll have negative 2 and negative 12. You'll have then negative 3 and negative 8. Then negative 4. And negative 6. If you keep going, your next pair is negative 6 and negative 4. But notice this pair and this pair are the same, so we don't need the negative 6 and negative 4. So we're just looking at these four. My next step is to find my sum. My sum means I am adding all of these pieces together to see what I get. Negative 1 plus negative 24 is negative 25. Negative 2 plus negative 12 is negative 14. Negative 3 plus negative 8 is negative 11, and negative 4 plus negative 6 is negative 10. The pair that I want to pick, the pair that I'm going to be using, is going to be my negative 3, and my negative 8 because when I added them, I got negative 11, which was the same thing as my b value. So I'm going to rewrite this problem as 6x squared minus 3x minus 8x plus 4. And remember that my 3 and my minus 3 and my minus 8 came from right here, the minus 3 and the minus 8 that were there. Now I can take the time to do my factoring. So I'm going to break down, and I do this in pieces, so I break down the first part. Well, 6x squared is 2 times 3, and then 2x's, minus 3 times x. So I'm going to look to see what these two pieces have in common. So notice they both have a 3 in them. I'm going to write that down. They both have an x in them. So I'm also going to write that down. So then my leftover pieces would be 2x and then minus. Notice I got rid of everything here, so I'm going to put a 1 as a placeholder. Then I'm always going to bring down my sign. This sign right here always comes down. And then I'm going to prime factor the other side. So 8. Well, let's see. I'm going to use this little space over here to the right. If I prime factor 8, 8 is 2 and 4 is 2 and 2. So 8 is really 2 times 2 times 2 times x plus 4 is just 2 times 2. So I'm looking for what these two pieces have in common. Well, they both have 2 2's in there, and 2 times 2 is 4. And then my leftover pieces are 2x. And then, so notice I put a minus sign on the outside, which means I'm going to change the sign on the inside. So it's no longer going to be plus. It's going to be a minus sign on the inside. And I got rid of everything here, so that tells me this is going to be a 1. And recall, we'll know if we did the problem correctly. This is just a way to check it. We'll know if we did the problem correctly if we look at our parentheses and they're exactly the same, which they are. So that tells me that my factorization is 3x minus 4 and 2x minus 1. Remember that the 2x minus 1 comes from what is inside the parentheses, and the 3x minus 4 comes from what is in front of the parentheses. That's where those pieces come from. So now that I've got this part down, remember this problem did equal 0 to begin with, so that here it equaled 0. So that means I'm going to take each of these pieces, so starting with 3x minus 4, I'm going to set it equal to 0. And then I'm going to do the same thing with the other pair. I'm going to take 2x minus 1 and set it equal to 0. And then I'm going to solve this. So I need to get x by itself, which means I want x's on one side, everything else on the other. So I need to get rid of this minus 4 first. I'm going to do that by adding 4 to both sides. So I end up with 3x equals 4. And then to get x completely alone, I'm going to divide both sides by 3. And I end up with x equals, I'm going to leave this as 4/3 because 4/3 is an ugly decimal. Do the same thing with the other part. So I'm going to draw my line. I want x's on one side, everything else on the other. So that means I need to get rid of the minus 1 first by adding 1 to both sides. So 2x equals 1. And then I'm going to divide both sides by 2, and I get x equals 1/2. And that is my final answer. So altogether, my answers are either x equals 4/3 or x equals 1/2. So problem 9 was a little bit different because it was easier in some ways and harder in others. So first of all, it doesn't equal 0, so I need to make sure that happens. So to get rid of this minus 2, I'm going to add 2 to both sides. I can't actually combine this 2 on the left with anything, so I'm going to have r squared minus 3r plus 2 equals 0. And then I'm going to identify my a, which is going to be 1. My b, which is going to be negative 3, and my c, which is going to be positive 2. And I'm going to use my table in y equals, so I'm going to do y equals 1 times 2 divided by x. And I'm going to look at my table. Notice that there was a negative sign in my problem, so I'm going to go look at my negative numbers. And the only set of negative numbers you're going to have is -1 and -2. And guess what? If you find the sum of -1 and -2, you're going to get -3. So I'm going to pause the video, work all this out, and then I want you to pause the video and then work all this out if you can. And I'm going to go ahead and pause it and work it out. And when you see it in a second, it will have everything done. So after I was able to factor this, I ended up with r minus 1 times r minus 2. And I set each of those pieces equal to 0 and solved, and I end up with answers of r equals 1 or r equals 2. So again, remember I color-coded all of my factoring was done in pink, so that was all these steps over here, and all of my solving was done in green, that was all these steps over here. So pay attention to the colors and that where they match up, and that will help you figure some stuff out. So we have 2 more problems to do. I'm actually going to do 11, and then I'll pause the video and then do 12. So 11, we're supposed to again factor. So when I do the factoring, as before, I'm going to do the factoring in pink, and then I'm going to be solving this, and I'll do all my solving in a shade of green. So the good thing is when I'm factoring these are the problems we just learned how to factor. Well, remember that x squared is just x times x, and 144 is 12 times 12. So the factorization of this problem is going to be x plus 12 times x minus 12, and it still equals 0. So then when I go to solve this, I'm going to take each parentheses, x plus 12, and set it equal to 0, and then do the same thing with the other parentheses, x minus 12, and set it equal to 0, and I'm going to solve. Well, to get x by itself for the first one, I'm going to minus 12 from both sides, and I'm going to get x equals -12. And then for the second one, to get x by itself, I'm going to add 12 to both sides, and I end up with x equals +12. So my 2 answers are x equals +12 or x equals -12. So for 12, the biggest thing here on this one is we've got to remember that we need to get this to be on the same side. So get rid of this 49. I'm going to minus 49 from both sides. So now my problem is 9y squared minus 49 equals 0, and this is a difference of perfect squares. So I'm going to pause the video, work it out. You should do the same. So when you factor this, you end up with 3y plus 7 and 3y minus 7. And after setting each of those pieces equal to 0 and solving, you end up with y equals -7/3 and y equals +7/3.